Hello, welcome to another module in this massive open online course. So, we are looking at the DFT, that is the discrete Fourier transform, alright, and its application for finite length discrete time sequence. Okay. So, we are looking at the discrete Fourier transform, which as I have already alluded to is one of the most important tools which has revolutionized signal processing. So, this is the discrete Fourier transform. Okay. So, we have already seen this is the DFT, okay. And in the DFT what we have is we have the DFT of the finite length sequence, and we are looking at the properties of the DFT. Let us continue our discussion with the properties. So, this is the next property, that is conjugation. So, we have a sequence x n which has the DFT, let us say x of k, then you can show that x conjugate of n, it is not very difficult to see, x conjugate of n has the DFT, that is x conjugate of minus k, but remember the minus k has to be interpreted as modulo n, alright. So, that is x conjugate of minus k modulo n. Okay. The next property is, again this is a very simple property which you can verify yourself. There is a frequency shift property, the frequency shift property, shift in time results in modulation in frequency. Naturally one can expect, as expected, modulation in time results in a shift in frequency. So, x n has the DFT x of k, then W n k naught of n x n has the DFT x k minus k naught. Okay. Then you have the duality, all right. So, x n has the DFT x of k. Now, what can we say about the sequence? Remember, duality is the time domain becomes frequency domain. What happens to the DFT of capital X of n? That is small x of n has the DFT capital coefficients given by capital X of k. What can we say about the DFT coefficients? What can we say about the DFT of the time domain coefficients given by capital X of n? And that is also fairly easy to see. We have, you just write it as capital small x of n. Remember, you can write it using the inverse DFT as 1 over n summation k equal to 0 to n minus 1 x k W n of minus k n, which is now you change. So, now if you look at x of, now you interchange n and k, replace n by k, interchange the rules of n and k, and then what you will have is I can simply write x of k equals 1 over n summation k equal to 0 to n minus 1, or in fact we are interchanging x and n and k. So, this is n equal to 0 capital N minus 1 x of n W n, and this remains minus n k, which is the same as minus k n. Okay. And now what I can do is, if I consider x of minus k, that becomes 1 over n summation n equal to 0 to n minus 1 x n w n raised to n k, okay, replacing it by minus k, okay, w n raised to n. And of course, the minus k is interpreted modulo n, and the final operation is to get the n to the other side, and that implies n x of minus k is basically summation n equal to 0 to n minus 1 capital X n w n to the power of n k, which is basically DFT of, you can see, x n. So, x n, the capital X n sequence, you can see has the DFT coefficients which are n x of minus k. Great. So, and of course, the minus k is, remember, everything is always interpreted modulo n. Okay. So, a capital X of n has the DFT discrete time Fourier transform coefficients given by capital N x of minus k. Okay. All right. And then the next property is also fairly important, which is a circular convolution. Which is basically x 1 circularly convolved with x 2, or x 1 circularly convolved with x 2 of n. This is basically equal to summation I equal to 0 to n minus 1 x I x 2 n minus I, but the n minus I has to be interpreted modulo n, okay, which is basically x for summation n equal to, so basically which is summation x I, so summation x I x 2 n minus I modulo n, okay. And now if you look at the DFT of this, we want to ask the question that we want to ask is x 1 of n circularly convolved with x 2 of n, what is the DFT of this quantity? And the DFT of this quantity can be found as follows. You have summation I equal to 0 to n minus 1, remember this is x 1 I, x 1 I x 2 n minus I w n k n summation n equal to 0 to n minus 1, that is basically your, or the DFT k, the DFT coefficient of the convolution, circular convolution of x 1 n circularly convolved with x 2 of n, all right. And now again, as usual, we interchange the order of summation. So, that gives us summation I equal to 0 to n minus 1 summation n equal to 0 to capital N minus 1. We have x. Now, the term with respect to I that comes outside. So, that is x 1 I summation I equal to 0 to n minus 1 x 2 n minus I w n of k n, and remember this is the shifted sequence, DFT of the shifted sequence. So, the x of n minus x 2 of n minus I. So, this is simply w n of k I times x 2 of k, okay. So, now we have this basically reduces to summation I equal to 0 to n minus 1 x 1 of I into w n of k I into x2 of k, and x2 of k is constant, depends only on k, and you can see this is nothing but x1 of k. So, that reduces to x1 of k times x2 of k, and this is something that is very important. Circular convolution of two finite length sequences, right, of equal length capital N, when you circularly convolve them, the DFT domain, the respective DFT coefficients get multiplied. In fact, this is a very important property. It is used in a practical wireless communication system. In fact, most of the all of the 4G phones that you use are based on the LTE standard, which uses OFDM, orthogonal frequency division multiplexing, which is based on this phenomenon, correct. So, we have two finite time domain sequences x1 n circularly convolved with x2 of n, and that basically has the DFT coefficients x1 k into multiplication in the DFT domain. Okay. So, these are the coefficients x1 k into x2 k, all right. So, circular convolution. So, this is, remember, this is your circular convolution, okay. Just so that you are not confused, one has to use the appropriate sense of convolution, correct. For periodic signals or finite length signals, it is always circular convolution. For infinite signals, it is always the linear convolution, all right. Okay. And on the other hand, when you have multiplication in the time domain, again as a dual property, multiplication in time okay. So, x1n into x2n that has the DFT, that is 1 over n, and you can show this x1 k circularly convolved with x2 k, because remember capital X1 capital X2 are also finite length DFT sequences. So, it is circular convolution between x1 k and x2 k divided by n. That is the rule for multiplication of two time domain signals. Okay. And now, we can derive the Parsevals relation from this. The Parsevals relation we can derive the Parsevals relation. Parsevals relation we can set x2 n equals x1 conjugate n. So, if you multiply x1 with x1 conjugate n, then we have magnitude x1 square, that has the Fourier transform 1 over n x1 x1 k, and the Fourier transform of x1 conjugate of n, that is x1 conjugate of minus k, which is, if you look at this, that is going to be summation 1 over I equal to 0 to n minus 1 x1 I x1 conjugate of minus k minus I, which means x1 conjugate of I minus k. Of course, the I minus k is modulo n. Okay. So, this is basically the Fourier transform of magnitude x1 square, which means if you look at summation of the kth DFT coefficient, summation of n equal to 0 to n minus 1, that is, if you look at the kth DFT coefficient of this magnitude x1 n square w n to the k n, this is the kth DFT coefficient of magnitude x1 n square. Remember, this is the kth DFT coefficient and this is equal to, remember, 1 over n summation I equal to 0 to n minus 1 x1 I x1 conjugate of I minus k. Now, in this both sides what we do now is you set k equal to 0. When you set k equal to 0, what I have is this reduces to wn raised to 0, which is 1. So, on the left hand side you have summation n equal to 0 to capital N minus 1 magnitude x1 n square. On the right hand side you have 1 over n summation I equal to 0 to n minus 1 x1 I into x1 conjugate I minus k, but k is 0. So, x1 I into x1 conjugate I, which is magnitude xi square, summation I equal to 0 to n minus 1 divided by n. So, that is your Parsevals relation. So, set k equal to 0, that gives you summation, that gives you something very interesting, just a very handy relation that gives you summation n equal to 0 to capital N minus 1 magnitude xn square x1 over n summation I equal to 0 to n minus 1 magnitude x1 I square, and this is the Parsevals relation for, this is the Parsevals relation for DFT. Okay. This is the Parsevals relation for DFT, discrete Fourier transform, all right, and that basically completes our discussion for the DFT, that is the discrete Fourier transform, all right. So, what we can do now is we can start looking at some example problems for the Fourier analysis of discrete time. So, we have some example problems. In fact, several example problems for Fourier analysis of discrete time signals. The Fourier analysis of discrete time signals. Let us start with the first problems first. Similar to our discussion here, we are going to start with the discrete Fourier series, proceed to the discrete time Fourier transform, and then ultimately the discrete Fourier transform, just the way we have covered this in the various modules. Okay. Let us look at a first problem, that is, consider a periodic signal period n naught equal to 0, which is even. Period n naught is even. So, xn equals 1 in a single period is given as xn equal to 1 for 0 less than or equal to n less than or equal to n naught over 2 minus 1, and it is 0 for n naught by 2 less than or equal to n less than or equal to n naught minus 1. So, this is basically description of it in a single period, and then it repeats. Okay. This is for one period n naught, and then again it repeats. Okay. Description for a single period. This is the description for a single period. Now, what is the discrete the DFS? What is the discrete Fourier series coefficients of xn? Now, we know that n naught is the period. So, the fundamental frequency omega naught can be defined as 2 pi by n naught, and the DFS coefficient is C k equals summation 1 over, remember the DFS coefficients are given as 1 over n summation n equal to 0 to capital N minus 1 x n e raised to minus j omega naught k n equals 1 over n naught summation n equal to 0 to, well, now it is only 1 from 0 to n naught by 2 minus 1. So, n naught by 2 minus 1 x n is 1 e raised to minus j omega naught k n, which is basically 1 over n naught 1 minus e raised to minus j omega naught k e raised to minus j omega naught k into n naught by 2 into over 1 minus e raised to minus j omega naught k. Okay. And now here in the numerator you can see omega naught equals 2 pi by n naught. So, omega naught n naught over 2 is basically simply pi. So, in the numerator I have basically this is your C k, left is C k, right is 1 over, the right hand side is 1 over n naught times 1 minus e raised to minus j omega naught n naught over 2 is pi 1 minus 1 minus e raised to minus j pi k 1 minus e raised to minus j omega naught k which is basically 1 over n naught e raised to minus j pi k divided by 2 e raised to minus j omega naught k divided by 2 e raised to minus j pi k over 2 minus e raised to, I am sorry, this is e raised to j pi k over 2 minus e raised to minus j pi k over 2, denominator e raised to minus j omega naught k over 2 or 1 e raised to j omega naught k over 2 minus e raised to minus j omega naught k over 2 which is basically, now you can simplify it this as 1 over n naught e raised to minus j k over 2 times pi minus omega naught times sin k pi over 2 divided by sin omega naught k over 2. That is your expression for so this is your expression for C k, that is the DFS, discrete Fourier series coefficient original periodic signal x n. Okay. All right. So, basically what you can, so basically what we have done in this module is we have completed our discussion of the DFT, the various properties of the DFT such as the duality, the convolution, the circular convolution, and also the Parsevals relation, followed by an example for the discrete Fourier series. So, we will stop here and look at other examples in the subsequent modules. Thank you very much.